All right, welcome everyone. So let me share the screen. Um, all right, hope you can see screen. And we have like 7 or 8 questions that I'm planning to discuss. So let me show you all. These are all calculus questions and practice question for your test 3. You can see yeah, 8 questions. I may discuss first 3 questions in this video, and I will, record maybe 1 or 2 other videos and go ahead and explain all the questions. Okay, right. So my suggestion is to practice more similar question like this and expose to more questions, and it will boost your confidence and you understand the concept, and you can perform better. Okay. You can use textbook questions, or if you need similar question, just let me know. Okay, right. So look at the first question. First question talk about finding this function has exactly one real root exist. Okay, so it's kind of a not the way you need to find the solution. You have to find the existence of the solution. So you have to show there's only one real root exist. So first, what you want to do, you want to explain there exists at least one solution. Okay, so to do that, we use something called intermediate value theorem, IVT. Okay, intermediate value theorem says if you can find two x values, for an example, here I can show you one x value which is -1. If you plug -1 to the function, these are all odd powers here. 51 is odd power. So if you plug -1, -1 to the odd power is -1, -1, x is -1, and you have +1. If you plug -1, you will get -2, which is negative number. And if you plug 0, for an example, you get 1. So that means I know, so let me show you maybe, oops. I'm going to get coordinates. So let's see this one. So now you can see if I choose 2 points like, oops, so this is 0, and this is my -1, and I know at -1 I got a -2 somewhere here, and 0 I got 1. So my function is, this function is a polynomial and smooth and differentiable and continuous. So function should go through these 2 points, which means it should cut the x-axis anyway. Otherwise, you can't go from, let's say, A to B. So there should be a root exist in between -1, 0. But we don't know, there may be more solution. We know there's exists at least one root here, but I want to show that that's the only root. So what I'm going to do is I'm going to take the derivative. If I take the derivative, it says this 51 x 50, and you get 1. You can see no matter what x I put here, this function is always positive. Okay, if you plug 0, it gives you 1. The first derivative will be 1. But if you put negative x, positive x, it's always positive. That means this function is always increasing. Okay, the function's derivative not equal to 0 means there's no way it's turning. There's no turning points. You can say it's increasing. This means function is increasing, no turning points. You can apply Rolle's theorem. That, for an example, you can say, okay, this is your point A. If there's another point, let's say B, which is also a root, we assume there's another root. So then you can see f of A, which is 0, is equal to f of B, because both A and B are roots, right? So if you plug those points to the function, you get a 0 actually. That means they are equal to each other. The Rolle's theorem says if the function equal at A and B, there should be a point C between A comma B. The derivative of the function at that point will be 0. But I know this is never equal to 0. This function is never equal to 0. That means there does not exist such C. There does not exist such C mean does not exist such B. Okay, that means there's no way function come back and cross the x-axis. Okay, so that's explain there exists exactly one real root, which is we identify somewhere here between -1 and 0. Okay, right, I think it's clear. You can apply the intermediate value theorem plus Rolle's. Or if you don't need to talk about Rolle's theorem much, you can at least show the derivative is positive, which means the function is monotonic and it's increasing forever. Function is increasing mean it's going like this. That's it. Okay? It's never, there's no turning points. Right, so I'm gonna erase that part. You can pause the video and write down and think about it a little more, and find similar question and work with that. Okay. Number 2, you have to use mean value theorem. In the mean value theorem, that the first part tells you a function. The suppose function f is an odd function. You have to use the property of being odd f. Okay, f is an odd function, and that's the condition for odd function. F of minus b equal minus of fb, and if it is an even function, f of minus b will be equal to f of b. If the function is an even function, if it is an odd function, there should be a minus here, right? So you can use the mean value theorem. It says f dash at c is equal to f of b minus f of minus b. Why? Because my interval, I choose negative b to positive b. So if we subtract negative b from b, it will be 2b. So this will be f of b. But I know f of minus b is equal to minus f of b. So that means it's become plus. Because if the minus coming out from this minus I can take out from the function, and this will be plus. One erase that way. And this is 2b, and I can find 2 of fb equal 2b, and I can cancel out 2, and I can find it's equal to f of b over. So that means we prove the condition that there exists a number c in minus b to b interval such that this condition satisfies. This condition, okay? This condition satisfies. Clear? Now, part C. Part C, it says at 2 p.m., a car's speedometer is 30 miles per hour. At 2:10, it's increase its velocity to 50. Okay. Show that at some time between 2 to 2:10, the acceleration of the car is exactly 120 miles per square hour. So this should be H2. Okay. So you can write the mean value theorem. Okay, let's say C is a time between 2 p.m. to 2:10. Okay, this is my time. Okay, I can take my function fx as velocity function because they're talking about velocities. Mean values theorem says the derivative of f at c can be written as f of 2:10. That's the velocity at 2:10 p.m. This is the velocity at 2 p.m. The gap between 2:10 to 2 is 10 minutes. Okay. So I know the velocity become 50 at 2 p.m. and I subtract 30. So this is in miles per hour. I'm gonna change this 10 minutes to hour. It's 1/6 hour. 10 minutes mean 1 out of 6 in hours. Okay, so it gives me 120 miles per square. So that means I don't know the time exactly the acceleration of the car become 120, but I can find, like the mean value theorem guaranteed that I can find such time c. Okay, this is actually acceleration. Okay, acceleration, because the derivative of the velocity, the fx is velocity, derivative of the velocity is acceleration. Okay, right. Okay, first question and second question we done. Third one, you need to find local minimum and maximum values of the function f. So let me start with, see if I can take a different color. How about green maybe? Yeah, here we go, that's good. You can take the second derivative and discuss the second derivative test if you want. And if you find very hard to take the second derivative, especially maybe this one, you could consider taking first derivative and talk about minimum maximum by discussing what happened to the first derivative at the neighborhood of the critical points. Okay, we will do both. We'll discuss all the concepts. So take the first derivative of the function, which is 6x to the power 2, 6x minus 2. It's the first derivative of the function f. I can take 6 out, and I have a quadratic function. This is easy to factorize. It's x minus 2, x plus 1. So critical points, to find the critical point, you set the derivative equal to 0, first derivative equal to 0. If you set that equal to 0, the x will be 2. That's one of the critical points. The other critical points you can get from setting x plus 1 equal to 0, which is x equal minus 1. Okay, so now I don't know those are like maximum, minimum, or even inflection point. To find that out, I take the second derivative, because this function is a polynomial. I can easily take the second derivative. Okay. Oops, I want to show you the part. If I take the second derivative, I'm going to take the first derivative and take one more derivative, this one. So I can take 6 out, and it will be 2x minus 1. Don't need to take the, you can find the inflection point, but they don't ask you to find inflection point there. Okay, local max and minimum. So if you plug 2 to your second derivative, if you plug 2, what happened? This is a positive. If you plug -1 to the function, it's negative. Second derivative positive mean add x equal to fx as, and you can say f the function. Normally we say f has minimum, local minimum. Okay. Second derivative negative mean at x equal -1, the -1 is here, see, f has local. This is the place the minimum happen. If you really need to find the minimum value, you need to go ahead and plug the 2 back to the function, but you don't need to do that, especially when you are taking the test. It takes a lot of time. It's enough to tell where the minimum and maximum occurs. Okay, so if it is a real application question, you need to plug the function 2 back to the function. And let me quickly find it for you. It's 16. I'm just plugging x equal to here, and you get 4, it's 12, it's 24, and plus 1, and it will give you -19. So 2, -19. This is the location or the point on this graph, you can x and y coordinate, and that's minus 19 is the minimum. It happened at 2. Similarly, you can plug minus 1 to the function, and you get minus 2, minus 3, plus 2, plus 1, and you get what? 7, 8 maybe? Yeah, it's 8. That is the maximum value. It happened at minus 1. Yeah. Yeah. You can write minus 1 combined. Okay. But specifically, I am looking for show these numbers. If you can find where the local mean and max occur, that's pretty much enough. Okay. How about the part B? Part B, x to the power 2 minus 1 cube. I'm going to write it here. Part B. My function is x to the power 2 minus 1. Is it cube? Yes, it's cube. Okay. And if you take the first derivative, you get 3 x to the power 2 minus 1, 2. You have to take the derivative of the inside, which is 2x. It gives you 6x, x to the power 2 minus 1 to the power 2. And if you set it equal to 0, it gives me two values, actually three values. X equals 0 you can get from this. This is, you can write x minus 1, x plus 1, because it's a square difference. So you have three critical values. Okay, three critical values. Right. If you want, you can go ahead and do the product rule and plug the point 0, 1, and minus 1 to the second derivative and discuss what is the local, where the local mean and max happen. Or you can do this. You plug minus 1 here. This is your 0. And this is your 1. And you can find out what happened to the first derivative less than minus 1. You can choose something like x equal minus 2. Let me use a different color for that. Okay. So I'm going to use x equal minus 2. It's less than this. Okay. So if I plug minus 2 here, this is always positive. Can you see that? This part is always positive. As long as you are not plugging 1 or minus 1, you are not going to plug those two numbers here. But if you plug something less than negative 1, it's like negative 2. So this is still positive because of the power 2. And this gives me negative, so it's negative. In between minus 1 and 0, like 0.5 negative, negative 0.5, it's still negative because this is the only contribution. And if you plug something like 0.5, it's positive, greater than 1, of course, positive. So this is like no change, no sign change at minus 1. So x equal minus 1 is really an inflection. Is an inflection. Okay. And this at less than 1 and greater than 1, no sign change. So it's, I can say at x equal 1 is also an inflection. What happened at 0? It decreasing and start to increase. So x equals 0 is a local. Zero is a local minimum. And you can easily plug 0 back to the function because this is the easy function to plug and you get minus. So the minimum point is 0, minus. The minimum value is minus 1. It happened at 0. Okay. I think it's clear. In this case, I didn't take the second derivative, but you could go ahead and do the product rule and discuss the same process we discussed over here. Okay, it's up to you. Find the local minimum and maximum using first or using the both first and second derivative. Okay, right. So I'm gonna go ahead and erase part A and try to do question number C, part C. Okay. It's a quotient, right? Quotient rule because it's a rational function. Numerator and denominator. We take the first derivative. Uh, take the numerator times the derivative of the, I'm sorry, take the denominator times the derivative of the numerator minus numerator times derivative of the denominator, which is 2x minus 1 over x to the power 2 minus x plus 1. Now you can see I have x to the power 2 minus x plus 1, 2 plus x over x to the power 2 minus x plus 1 to the power 2. If you simplify it, it's the numerator becomes 2x to the power 2, x and plus cancel out, you have plus 1. This will be to the power 2 minus x plus 1. Okay. If you think about the numerator, it's minus 2x to the power 2, 1. Denominator is a quadratic function, square. The nice thing about this is you don't want to worry about the denominator being equal to 0. This x to the power 2 minus x plus 1 never equal to 0 for any real x. Okay? There's no way you can factorize or find x value using quadratic formula. Okay? The reason is if you think about the discriminant, it's negative. Discriminant negative mean this function go above the x-axis, so there's no real root or real solutions. So no worry about denominator. I'm only concerned about the numerator. So numerator become, if I set it equal to 0, oh, this is, that's what I'm just wondering. If this is actually become minus, okay? So this is minus. This is negative 2, and you have positive 1. Yeah. Set this equal to 0, it's equal 1 or minus 1. Those are your critical points, okay? You can take the second derivative, or I think you don't need to take the second derivative to discuss local min and max, because it's again, you have to use quotient rule. So I'm not going to do that. Instead, I'm going to discuss what happened around this one. So I can choose something like -2 and plug. So this is, I don't care about the bottom, the denominator. So it means a different color. Very bad. Here we go. So I don't care about that part. If I plug -2 to this, it's always negative because of the negative. So it's like -4 plus 1, it's negative. If I plug like 0 for here, it's positive. If I plug like 3, again negative. So decreasing and increasing. So -1 is a minimum. Increasing and decreasing. This is at x equal 1, the function has a local maximum. Okay, right. So good. Right, last one, the trig function. So I'm going to do that. So the derivative of cosine negative sine, derivative of sine cosine, but I know it's just a 2t, so I have to multiply by the derivative of 2t is 2. So it's like first derivative negative sine t, this is plus cosine 2t times. In trig, we know there's an identity, like you can call it a half angle formula, some people call double angle formula. So it's 1 minus 2 sine square t. You know, the angle become half here. 2t become t. So I'm going to plug that here because I need to bring my first derivative to one same trigonometric ratio, not sine cos, only to sine. Okay. Oops, this is 1 square t, but I have a 2 here, so I'm going to multiply everything. Okay, so it will be negative 4, is it? Yeah. Yeah. Negative 4 sine square derivative of cosine is negative sine. Yeah, cosine 2t2. Negative 4 sine square t, negative 2 t, I have positive 2. If I take negative 2 out, it will be 2 sine square t minus become plus sine t minus 1. Okay, I take the negative 2 out, and I'm going to factorize my quadratic function. This is actually quadratic function in terms of not x, but sine x. I'm going to write 2 sine t with sine t, because if you multiply sine t with 2 sine t with sine t, you can get that 2 sine squared. So I need to get sine t, just sine t. So I'm going to put plus 1 here, minus 1 here. The minus 1 times 1 is minus 1. Cross multiply, for an example, if we multiply this with this, it's 2 sine t. This is minus sine t. So it's cancelled out and I can get plus sine t. So that's how you factor the first derivative. So once you have factors in the first derivative, you can find the critical points by setting first factor equal to 0. This gives me sine t equal half. The other factor is sine t plus 1 equal 0. So I'm talking about this one. Okay. Go to 0, and this one equals 0. Sine t can be half for many t values like 30, 150. You can go all the way to 360 degree and come back like 390. It's so many angles, but let's stick with like at least for 0 to 2 pi. Like, okay, like you can consider only one period. So there are 2 t values you can get. The sine value become half, which is 5/6, which is 30 degree, and 150, which is in the second quadrant, it's 5 pi/6. Both these angles, the sine value at both of these angles, sine value is half. There's only situation sine t become minus 1. So this is really sine t become minus 1. If you remember the sine graph, quickly remind, this happened at 270, which is 3/5/2. Okay. Right. Now, I'm going to take the second derivative. I'm going to take the second derivative and talk about what happened at these points. Okay. So let me take the second derivative. To take the second derivative, I'm going to use this one. So it's 2 cosine t, but it's minus. And if you take the derivative of this, it's like negative 2 sine 2t, but you have 2 here, so it's become 4. Cosine is minus sine 2t times 2. 2 times 2 will be 4. Okay, right. Now I found 3 critical points within 0 to 2 pi. I'm going to plug each of my critical points to the function. Okay, so f double dash 5 over 3, 5 over 6. I know cosine 5 over 6 is a root 3 over 2, so it's become negative root 3. Cosine 30 is root 3 over 2, okay? And if you put 30 here, it's become 60. Sine 60 is root 3 over 2 again. So this is a negative number. You get the negative. Actually, the value doesn't matter. The sign plus minus is the matter here. So if you get the second derivative negative, mean add 5 over 6, f has a local max. Okay, local max. The second derivative negative mean concave down. Concave down mean you have a maximum. Okay, right. What happens if you plug 5 pi over 6? I want to explain that one as well. Okay, 5 pi over 6 mean 150 degree. Here cosine is negative in the second quadrant. So overall, this number, I can even tell you what is the cosine pi 5 over 6 is like a negative 2 root 3 over 2, but it's negative. It's same as cosine 30, but it's negative. Here, 4 sine, so you multiply this by 2, it's 5 pi over 3. 5 over 3, because you multiply this by 2. So 6 become 3. So it's really 300 degree. Sine 300 is same as sine 60, which is root 3 over 2, but in the fourth quadrant, it's negative. So overall, it's like a positive number. So that point is local minimum. Because second derivative at 5 over 6 is positive, right? Finally, you have to plug 3 5 over 4, 2. Second derivative at 3 5 over 2. What happens if you plug 3 5 over 2 for cosine? Cosine 270 is 0. Sine, actually 2. If you multiply 3 5 over 2 by 2, sine 3 5 is again 0. So at that point, you have an inflection point. It's not a minimum or maximum. Okay, so there's one max and mean within 0 to 2 pi. The minimum happen at 5 over 5 over 6. Max happen at 5 over 6. It's really important that you familiar with some trig as well. Mainly I mostly focus on rational function and polynomials, but maybe you could get something with trig. Probably what as I mentioned, you get few questions and you have flexibility to choose. If you feel like trig function is hard to handle, you can skip it and work on other functions. So if you really prefer to work with that, go ahead. It's challenging and interesting. Okay. Let me see what's the time. So okay, 4. Now I'm going to explain number 4 as well because it's not too 6, 4, 5, 4, 5. Yeah, that's good. Okay. Let's do that. So first derivative is given. First derivative is given mean you just need to set it equal to 0 to find the critical points. Actually, it's easier because you don't need to even take the first derivative. Okay, so set the first derivative equal to 0 to find the critical. It will give me 7 minus 1 and minus 5. It's all I get from these factors. And what interval it's increasing, decreasing, and so on. So for part B, what I can do, similar to the third question, some cases you take the second derivative. You could go ahead and take second derivative here if you want, but it's a three products. It's tricky, but I think it's easy to discuss what happened in between of those values, because you have to discuss increase in decreasing part. So I think it's easy. We'll go with -5. This is -1 and 7. And you can write down some numbers less than -5, like -6, something like -2, 0 here, maybe 8 here. And if you plug -6 to here, it's like, so I'm going to write it. It's like, so let me write it here. -6 give you minus times minus times minus. It's overall minus. First derivative is negative, mean function is decreasing. If you plug -2 here, -2 will give me negative, negative, positive. It's overall positive. It's increasing. If you plug 0 to the first derivative, it's negative, positive, positive, overall negative. It's decreasing. If you plug 8 to the function, it's plus, plus, plus. So the interval, the function is increasing. If increasing on is -5 to -1, union 7 to infinity. That's how you here. F is decreasing on, it's decreasing on negative infinity to -5, union -1 to 7. Here, negative infinity to -5, decreasing from -1 to 7. And look at the sign change, and you can discuss where the local max occurs. Local max at x equal. The max happen when increasing and decreasing. So this situation. Increasing and then decreasing, -2. Decreasing and increasing, this is a minimum, this is a minimum. So local mean is equal -6. I'm sorry, this is not -2. Actually, this is -1. Okay. This is a minimum. 7 is also a minimum. So not -5, -6, -5 and 7. Those are the critical points. You have to talk about those. Each, 7 -1 -5 are the critical points. Those are the things that gonna be local max or min. So all the other points I used to discuss what happened less than and greater than or around the critical points. Okay, right. Now part B. How do you do part B? Part B, you can use the same technique, like find out where the numerator becomes 0. Look at that, -1 and 3 cannot happen. So you don't want to worry about that. Make sure you don't plug those values because it will give your first derivative does not exist situation. So I can get -4 and 2. Those are the critical points. Okay, those are the critical points. I can plug the values like -5 less than that. Maybe this is like 0. Here I can plug like 3. In the first derivative, If you plug -5 for an example here, okay, so this is one more thing. I have to include the situation like minus. I'm not going to plug that, but I'm going to use the -1 and 3, and I'm going to mark it here. Okay, so let me mark all those, because those will change my sign of the first derivative, those around those points. So I'm going to choose not only 2 and -4. This is my -4, and I have -1 here, and this is my 2, this is my 3. It should not be according to the scales, just negative to positive. Okay, I include -1 and 3 as well. And I have -4 and 2. So now I'm going to plug something like -5. It gives me minus to the top, minus again. Bottom is minus, and down will be also minus. Overall, it's positive. How about if I plug something like -2? If I plug -2, it's negative, positive, negative, negative. I'm using the factors, and I just write down what happened if I plug -2. If I plug -2 to my x minus 2, if I replace with this with negative, it's -4. I know that. That's why I write negative. The negative number. I don't worry about the number. So not some negative number. Some negative number times positive number is a negative number. Divide by this is positive, it will be positive again. If I plug -2, it will be here, positive. Negative. I'm sorry, because it's a top negative. Okay, this is negative. If I plug something like 0, what happens if I plug 0? If I plug 0, I would get negative number for the first factor here. Other one is positive. If I plug 0, it's positive because it's just 1. And this is -3, so it's a negative number. So overall positive. So this is positive. Greater than 2 and 3, between 2 and 3, I can choose 2.5. If I plug 2.5, I get plus here for the first one, plus. This is plus again, 2.5. This is a negative. So it's a negative. Greater than 3, like x equal 4, will give me all positive. You can double check. Okay. That's how the sign change of f dash. So f is increasing, decreasing, increasing, decreasing, and increasing. So at I know at x equal -4, this point, increase into decrease, this is 2. Both are max, local max. Okay. See if I any mistake. If I put 0, what happened? It's negative, positive. That's right. If I put like -2, it's negative, negative. I can see it's negative. Right. Yeah, I'll double check. Okay, so because I want to see what's going on one more time. So if I plug -5, negative, 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 and negative. So overall positive, that's right. This is good. -2 will give me negative, positive, -2 will give me negative. Both negative, so it's negative, that's right. 0 will give me negative, positive, positive, negative, so it's positive. Right. Yeah, so you don't want to talk about what happened at -1 and 3 because it's not in the domain, okay? Because those are vertical asymptotes. Yeah. From -4 to -1, it's decreasing. And yeah, -1 is decreasing. Yeah, it's interesting. Okay. So let us see how the graph looks like. Okay, I'm going to share that with you. So you see, I will stop sharing. Oops, let's stop sharing. Let me share it again. Okay, I'm going to share that. I want to double check. What is the function? It's x -2 plus 4 minus +1 -2, right? -2 plus 4 divided by 3 plus 4 plus 1 minus 3 plus 1. This is -3. Let me see. X plus 1 and x -3. So I got the -4 and 2. We have local max. -4 and oh, that's interesting. -2 x plus 4 x plus 1 -3. -1 is a critical point. Okay. But it's still -4 isn't a max or min. Similarly, 2 isn't a max or min. I want to check. I think this is really, I made a mistake. So let me double check, okay? I'm gonna, yeah, let's see. If I plug -5, what happened really? If I plug -5, this is minus, I'm talking about first derivative, -5 give me minus, and this is minus, all minus, this is correct, plus is okay. If I plug something greater than like -2, it gives me minus, plus, -2 will give me minus, minus. -5, -2. The sign change is plus to minus. It's just strange. I plug, for example, minus 5, minus and minus whole plus, that's right. If I plug minus 2, something greater than minus 4. Because if you see the graph, I can clearly see at minus 4, oh, I see, this is not the graph. Okay, that's my mistake. This is not the graph. It's a first derivative. All right. I mess up. This is totally correct. Okay, so this is my mistake that I think it as a function. It's not a function. It's a first derivative. All right. So this is a minimum, like we discussed, is correct. Okay. So I confuse. Okay. So we are not talking about the function. It is a first derivative. So I try to draw the graph of the first derivative. So it's totally mistake. Okay, so what we did uh, so far is correct. So we got minus 4 and 2 as our local max. Okay, and also minus at minus 1 and 3 we have of course we could get like decreasing and increases a minimum, local minimums. Okay, minus 1 and 3. Okay. Um, At those points, the second derivative, first derivative does not exist, but still, let me see. Yeah, you don't want to talk about those at those points because first, second derivative does not exist, mean it's not differentiable at those points. Okay, so you can ignore discussing minus 1 and 3. But minus 4 and 2 is clearly local max. Okay, right. Sorry about that. Showing the graph, it's not the original function of the original graph. It's the derivative graph. It doesn't explain what we are looking for. Right? So part C, um, again the first derivative is given, so you can erase that. C, you set the first derivative equal to 0, and you get sine x equal to 1 using the first factor, cosine x equal to minus. There are two x values you can get within this interval, or no, only one x value you can get for sine x equal 1, which is 5 over 2, 90 degree. Cosine will be minus half in second and third quadrant. Cosine is normally half, which is in 60 degree. So it's like 180 minus 60, which is 2 pi over 3, 120. So one angle is 120. At 120, cosine 120 is minus half. And the other one is 180 plus 60, which is 240. So those are the critical points. Okay. But in this case, again, you have to think about what happening in between. Okay, because you can go ahead and take the second derivative if you want, but I think it's clear that you can plug. This is my 2 pi over 3, which is 120. Oh, this is, I have to put 90 first. 90 is the smallest number. This is 4 pi over. Right. So how do you talk about? So remember, so I might not write all the information like where it's increasing, decreasing, but you can get that, once I say, and you just need to include the interval. You write down this interval notation, right? So if the original f dash, I'm talking about the first derivative, plug something less than 90 degree, like 60 degree, maybe 30, 60. Here you go. So if you plug 5/3 for here, it's, sin x is always less than 1. So it's always negative for anything. This is always negative. Cosine 60 is half. So this is plus. So it's overall negative. Right. How do you find something? This is always negative. The first factor is always negative. If you plug, for an example, at this point it's 0. That's the minus half. Anything less than that, the cosine value is greater than minus half. So you get something like less minus. So it will be positive again. Okay. It's like -1/3 for an example. Okay. It's, greater than minus half mean like -1/3 or something. So it's like something you get less than 1, greater than -1. Okay, so that's overall it's positive again. In between these two, like 180, if you plug sine, it's always negative, I told you. So cosine 180 is -1, so it's -2 plus 1 is a negative. So here it's become plus. Okay. More than that, I can plug something like 270. So first factor is always negative. Cosine 270 is 0. It's plus again. So it's a plus, negative. So based on that, I can say this is decreasing, increasing. This is local mean. This is increasing to decreasing. This is local max. This is the point of inflection. Okay, at 2/5/3. This is 120, 90 to 120. I can't plug really a value like, that's why I choose like, it's a little tricky to understand what's going on in between here to here. So let me, maybe if I remind you, that's what's happening. First factor is always negative. I'm talking about this one. Let's think about this. 2 cosine, like angle here, I can choose like 100 degree or 110 because I want to choose something 90 to 120. Like choose, if you find this value, I have +1. You can see cosine 120 is -1/2. So if the angle is smaller for cosine like 100, the value is more than this. So it's like -1/3. So if you simply, I'm not telling exactly the value, okay? It's not cos 100. Cos 100 is not -1/3, but I want to say it's something greater than this. Okay, so if you plug that back, you can clearly see this is a positive number. So it's like minus time. Oh, minus times. Let me see. -1/2 gives you 0 if you plug this cosine 100. Cosine 100 is yeah. All right. All right. I think this is clear. So I'll discuss number 4 and other question in a separate video. Okay. Yeah, I think that's good. So we'll take. Thank you.